So maybe you are already acquainted with what is learning techniques, mainly the supervised learning techniques. So you might have seen few examples uh, about what is called supervised learning. So like human learning from past experiences, the computer does not have experience. So therefore, a computer system learns from the data that we supply to it. So that is what is called past experience for the computer systems. So when it learns from the data to classify some objects, then we say that is what is example of supervised learning. It is supervised because you supervise the system using the data. So they are the focus. The primary focus is how to learn a target function that can be used to predict the values of discrete class attributes. For example, the loan should be approved or loan should not be approved based on your credit score. So high risk or low risk of a heart attack to a patient. So those are discrete classes. So the task is commonly called supervised learning. Also, we call this classification and regression techniques. So there are many examples. One such example can be a credit card company receives thousands of applications for new cards, and each application contains information about an applicant. For example, the applicant age, the marital status, his annual income, can be the outstanding debts or loans, then credit score rating, etc. Right? Then job profile. Then the problem you can formulate is how to decide whether an applicant should be approved or to classify applications into two categories: approved or not approved, whether the credit card company should give you a credit card or should not give you a credit card, right? So how can a company decide that? How can a bank decide that? So that is one of the application of supervised learning. They are based upon the past data. For example, age, marital status, annual income. You might have already supplied credit cards to several customers. So based on the past data, you have a model. The model can predict whether you have to approve or not approve. Then uh, what is then unsupervised learning? Because supervised learning, you might have a fair bit of idea by now. So imagine when you are flying over a city. So you can when you are about to land on the city, so you can see the ground levels. So there you can easily identify the forest area, the commercial places, farmlands, riverbeds, etc., based on their features without any explicit training. Let's say you have never visited that city, you do not know the topological distribution of the city, but still, if a drone image is provided to you, you can easily find out which area can be possibly farmland, if there is road network, that also can be identified. Commercial buildings can be easily identified, right? The residential area you can identify by looking at a drone image of any of the cities. So how do you know, even though you do not even know the name of the city, but still you can able to identify? So that is what, without knowing any data, available data, still you can past data, sorry. So you can able to identify the different regions of a city. So that is one example of unsupervised learning. So here the class levels of the data are unknown, means past experience is not given to you. Then how, given a new data, how to identify how many different classes exist inside the data. So that is what is example of cluster analysis. So mathematically, suppose set of data objects are given. The set of data objects means, let's say, for a credit card, it's all about the person's income, it's his annual income, his age, his marital status, etc. So then there are several features, or we also call dimensions. So finding groups of objects such that the objects in a group are highly similar or related to one another and different from or unrelated to the objects in other groups. So in this particular example, if you look at it here, so here, this is a two-dimensional plane, x and y axis, and some data points are given here. Some two-dimensional data points are given here and here. So which two data points are more closer to each other and which data points are far apart from each other? So if you look at these two data points, let's say you say these are more closer to each other than this point and this data points, right? So you say these two data points are more closer to each other as compared to the data and this data point. Therefore, so if you form the groups, these two data points most likely to be put inside a single group as compared to these two data points, right? So here there are two objective criteria. The first objective criteria is how to minimize the intra-cluster distances. So if you say this, the distance between two data points here, distance between two data points here, so we say they are more similar to each other if the distance between them is very less, right? So we'll also define what is the distance, or we call what is dissimilarity or similarity between two data points. But right now, let us assume the distance between two data points should be as less as possible within a group, right? And the distance between two different groups should be as more as possible. So that is the next objective criteria. So this way, the two objective criteria to identify the clusters, inherent clusters hidden in the data are intra-cluster distances should be minimized. That means the distances between the data points within a cluster should be as less as possible, and the distance between data points between two clusters should be as more as possible. So that is called intra-cluster distances should be maximized and inter-cluster distances should be minimized. So there are many real-life applications exist. One such very easy application is, let's say, retail company may collect the following information on households, like the annual income of households, then household size, how many members are there in the household, occupation of households head, distance from nearest urban area, whether this is a rural area or it's urban area. So depending upon that, they can identify in the following clusters. So this is what is your data, let's say for the Jabalpur city, for all the households, a company can collect all such information, and based on this information, they can make the households into different groups. Let's say 4 different groups of households can be formed. So in the first group, let us say you have small families and small families but are high spenders, and the second group can be large family with again high spenders, and the third group can be small family with low spenders, and similarly large family and low spenders. So if they have to sell a product, so which kind of products can be uh, they can send personalized advertisements to which set of groups. So let's say a company like LG wants to sell its products, so which kind of products they can recommend to cluster 1, cluster 2, cluster 3, or set of families in cluster 4. So since cluster 1 contains small family with high spenders, so probably if you want to, let's say the company wants to sell a refrigerator, so you will probably will send them some recommendation with a smaller size refrigerator having lots of features, loaded of features, and cost should be higher. And if it is for set of families in cluster 2, so they can recommend some products, some refrigerators having large size, having loaded of features, and cost should be more. And if similarly they want to recommend to families in cluster 4, so this is a large family but they cannot afford more money to buy the products, so they can send the product like a larger size refrigerator, but cost having lesser number of features, and the cost should be as less as possible. So this way the cluster analysis can be used for marketing purpose. So another nice example is document clustering. This is part of the called the natural language processing problem. So you might have heard about document clustering. Every day you open your Google News, so you find several recommendations. So if you read five, six, let's say sports related news, so next day you see your Google alert is full of only sports related news. So if you open some news related to, let's say, finance, so next few days you will only find news related to finance only is recommended to you in your mobile phone. So how does the Google find the related news items? So there must be a group of news items. For example, some set of items, articles published in today's newspapers, which are related to sports, which are related to, let's say, politics, which are related to finance, right? So then a given set of documents, all set of news articles published today, let's say, all about the world, can you able to categorize such news articles? So that is what is the problem called document clustering. So we cluster, we form the groups of news articles, related news articles. So if it is a sports article, so you can group all the sports related articles in a group. And if a person reads one or two articles from that group, you know that the person is more interested to know about the sports activities happening all over the world. So the system started recommending only the news articles which are related to sports. So next day if you open some finance related articles, what is happening in the market, then probably which share is going up, which share is going down. So probably next few days you will find many articles related to only share market, right? So this is one example of again clustering problem, where the set of data items are the rule are the news articles, and based upon the terms in the news article, let's say sports related terms, if you find Tendulkar, let's say, appears several times in news article, so most likely that news article is related to sports, right? So you keep that in a sports related article. So that is how we form the groups hidden in the data without doing any training or past data. So this has a long history, and the clustering is used in almost every field, for let it be medicine, botany, sociology, biology, marketing, insurance, libraries, etc., etc. There are many applications. So we'll today's talk we will not see more about the applications. We'll see the fundamentals of clustering algorithm. So once you know a few clustering algorithms, those you can be applicable to any domain. So what is not then clustering? Making the groups you might have encountered in many applications. As a faculty, you might have many ways divided your students into different groups. For example, based on their registration or alphabetically, you can might have formed the groups, right? Or based on their skill set, you might have divided the students into different groups, different sections, right? So based on the language they speak, they know, you might have divided them into groups, but those are actually not examples of clustering, right? So this is simple segmentation based upon some external criteria. You are dividing the group. So therefore that is not an example of a clustering problem. Results of a query, let's say we have set of employees. So tomorrow, if you go and ask how many of the employees earn more than 12 lakhs per annum, so you give me a set of persons which earn more than 12 lakhs per annum, and which set of employees has a earning less than 12 lakhs per annum. So you can easily identify such people based on their pay slip, right? So that is just a query and its answer. So that is not one example of clustering problem. Then obviously the supervised classifications, where they are also giving the data, you can classify the objects into approved or not approved, prone to heart disease or not prone to disease, like classes. So those are also not examples of clustering, because they are the proper training of the past data is done uh, using a model. So that is also not example of clustering. So, what is the notion of clustering? So, it can be highly ambiguous depending upon your application. So, given these two-dimensional data points, several data points you can see here. So, given these data points, If I ask you in your naked eye, tell me how many clusters you can identify in this data, how many groups of objects, how many groups are closer to each other, how many groups are not closer to each other. So how can you identify how many clusters are present in this data? So that is highly ambiguous. Somebody can tell that clearly it is only two clusters. So these two are the clusters from this data. This set of data points forms one cluster. This because they are highly separated between them. So there can be two cluster. Somebody can say, no, this is not actually two. This can be six clusters. You can see here each color represents one cluster. So this is one, three cluster. Here also three clusters. So somebody else can say probably no, it can be four clusters. So again, the shape says here represents one cluster. So this is one cluster, this is one more, and this is probably the fourth cluster. So this way, which one then is the best cluster or the proper cluster? Actually, it's a difficult things to answer. That many ways you can form the cluster, right? But then once you form the cluster, whether the real or actual clusters are formed, how do we know this, right? So those are that, therefore forming the clusters is highly ambiguous in nature. So there are many challenges. So aspect of clustering is how to form good clusters. So first criteria is there are many clustering algorithms exist. So using such algorithms, we can form the clusters. So we'll see one or two algorithms in today's lecture. So that is one of the aspects of clustering which influences the clustering techniques, how to form good clusters. So that depends upon which clustering algorithm you are going to use. Then the second aspects of clustering which can influence the clustering process is the proximity function, or we call similarity or dissimilarity function. Then the third aspect is once the clusters are formed, so how good the clusters are, right? So that is called measuring the clustering quality. So you buy a dress, then you say how good your dress is, right? Based upon the maybe the quality of your fabric, its cost of your dress, etc., etc., right? So based on that you decide whether the quality of your dress is good or bad, right? So quality of a product is good or that you use, and then say that it's a bad quality product, it's a good quality product. So there are certain parameters, depending upon that we decide if a product is good or quality of the product is good or quality of the product is bad. So here once the clusters are formed, so how can we say which set of clusters are good or which set of clusters are not good? So the quality of a clustering results depends on the algorithm, the proximity function, and the application. So in today's lecture, we'll see all three aspects. So first and the simplest one is the proximity or distance function. So we'll start with the distance function, then we'll move to the clustering quality, and finally we'll see one or two clustering algorithms. So if I say out of a bunch of people, let's say faculties, if I say which two faculties are more closer to each other and which two faculties are not very close to each other. So how do we measure the closeness of two persons, right? So one of the things can be they sit their offices are very nearby to each other. You say they are more closer to each other, so that is what is the physical distance, the Euclidean distance we say. We know how to measure the distance, right? Given the xy coordinate of two places, x1 and y1 and x2 and y2 from our school days, we know how to find the distance between them, right? So Euclidean distance. So other can be their characters, how do they behave, right? Their annual income, the way they appear in the public, their food choices, their dress choices, and so many things, right? Based upon that, we say we are more compatible with each other and we are not compatible with each other. This is how human beings treat ourselves, like we are similar or we are dissimilar, right? So we form our families based on that. So then given the data objects, how to find which to, can we quantify that, right? in terms, in numerically, can we quantify the human similarity? Which two humans are more similar to each other than other persons? So can you quantify by looking at, we have our own data, we have our past experiences. So using our own past experiences, so that is what the way we are trained. So based upon our training, we say these two are more similar, right? They are more compatible, and those are not compatible, right? But if I say, give me a number, how much, what is the percentage of compatibility between two persons? Can you able to give me a percentage, right? So what is the percent? It's a 90% compatibility, 100% compatibility, 50% compatibility. So what is, can you give me a value numerically? It's a difficult thing to say. You must have a formula to find out numerically which two are more compatible to each other, and so on, right? So similarly, numerical measure of how alike or similar two data objects are. So value is higher when objects are more alike to each other, and that often falls in the range 0 to 1, right? We say sometimes in the range of 0 to 1, 1 means highly similar, 0 means highly dissimilar, and some value 0.5 in 50% similarity, zero point 0.7 is 70% similarity, and so on. So what is this similarity? It's just the opposite of similarity. So that is numerical measure of how different two data objects are. So lower when objects are more alike, minimum dissimilarity is often 0, upper limit varies. We'll see the example. So when you say proximity, that refers to similarity or dissimilarity. This is more of a generic terms to represent similarity and dissimilarity. When you actually do not know whether the function is a similarity function or a dissimilarity function, we better say it's a proximity measure. So data matrix you might have already seen in many of your applications. If you have run the Python code, you might have given lots of data as input. It can be image data, it can be text data. So that is basically the data objects are represented as rows in the in a matrix. So it's a n cross p matrix. So where is n? So it's object 1, then it is object 2 is in row, object 3, object 4, right? So what are the columns? The features. The feature 1, this is feature 2 up to feature p. So each feature is also sometimes called a dimension of the data. So it's a p-dimensional data, right? So this kind of matrices are called data matrix. So what is dissimilarity matrix? So this is again n data points. So each data point is represented as a row, and what the column represent? The column represents the distance between two data objects. So what is the distance between data objects 1 1? So that is d11. So d11, the data objects with itself, the distance is obviously 0. So what is the distance between data objects 2 and 1? So that is represented as d21. So what is d31? Data objects 3 and 1, then data objects 3 and data object 2, data objects 3 3 is 0. So obviously it's a triangular matrix. So upper triangular is same as the lower triangular. Therefore, only one triangular part, lower triangular part is shown here. So that is the fundamental difference between a data matrix. So data matrix is always a n cross p matrix, where n is a data number of objects in your data, and p is the number of features or dimension of the data, right? And the similarity matrix is always a n cross n matrix. Why n cross n? Because number of rows is n, number of columns is also n. So that a number of rows and number of columns represents each and every data point. So therefore it is always a n cross n matrix. So what is the distance function? So that you already know, you from our school days we have learned distance function, many distance functions. So we'll see today very simple examples that we have already seen from our school days. So the key to clustering is similarity and dissimilarity. So there are several dissimilarity functions. There are different types of data depending upon the data values or the feature values. So the well-known data or widely used data that we human beings are more acquainted with is numeric data. For example, we say what is the height of a person, what is the weight of the person, what is the quantity of, let's say, wheat, what is the quantity of rice, right? So what is the price of a t-shirt, what is the price of your car. So all these are examples of numerical data which you represents numerically, let's say 5.5, 10.10, what is your annual income. So all those are examples of numerical data. There are also another kind of data called categorical data. In the categorical data are actually discrete values. They are not numeric values. Though you can see the numeric values there, but actually those are coded, just some kind of code. So that is, if the data is nothing but codes, then we say those are categorical data. So what is nominal data? The categorical data again can be classified into two categories: nominal data and ordinal data. What is nominal data? For example, gender is male and female, so it is just a code, right? So those numbers cannot be comparable, right? So you cannot say male is lesser than female, male is better than female, male is lesser than female. So no way you can compare between them. So those are the codes which are uncomparable to each other. Those kind of data is called nominal data. Another example is your blood groups: AB, O. So who is, we cannot say A blood group is superior than B, A is better than B, A is less than B, A is greater than B, A is higher than B, A is lower than B. So those kind of comparisons are not possible. Those are just some kind of coded data. So those, if the data is like that, that is called nominal data. What is ordinal data? That categorical data are codes when they are comparable with each other. Those kind of data is called ordinal data. So what is the size of the t-shirt? Right, small, medium, large, XL and double XL. So here those are simple codes, but then the speciality about this code is they are comparable codes. So the size of the smaller size t-shirt is lesser than the size of a medium size t-shirt. So now I can able to make a comparison. The size of S is size of M size is less than L size is less than XL, and so on, right? Similarly, the grades that we provide to the students: A plus A, B plus B, C plus C, D plus D, and F grades. So what is so now again we can able to compare: A plus grade is better than the grade A grade is better than B plus, and so on. So therefore, this is one example of ordinal data. So depending upon what kind of data, is it numerical data, the similarity measures are different. If it is categorical data, numerical measures are different. Again, within categorical data, if it is only nominal, the measures are different. If it is only ordinal, measures are different. If it contains both nominal and ordinal, again you have to treat them separately. So you have to use different kind of similarity function. Your data may already contain numerical as well as categorical. So those kind of data are called mixed data, right? That contains both nominal and categorical. So again, there is an issue. You have to find out some similarity function which are applicable for mixed data. So let us, for sake of simplicity, we will only use numerical data examples. So in the proximity measure, let's say suppose xi and yi denote the value of the ith attribute of objects. Let's say object x. Now, so how do we represent object x? So object x is 1 minute, please. Is x1, x2 up to, let's say, xp. Here it is n, let's say xn, and there is another object y which is let's say y1, y2 up to, let's say, yn. So now we define the distance function between them: xi minus yi. So this is my attribute 1, this is my attribute of feature 2, this is my nth attribute or nth dimension. Now x1 minus y1, right, to the power r, take the sum of this and then whole to the power 1 by r. Okay, so this is what is called, r is any integer value here. So this kind of distance function, this is set of distance functions, is called Minkowski metric. You might have heard about Minkowski metrics. Let us see some special kind of functions, which is easy to understand. So again, you might have studied already what is called a metric. We will not go deeper into it in the today's lecture. So some distance function can be non-negative values. Always you find the distance between 2 points. In our school days, we know when you give in x and y coordinate of two points, let's say the points are IIITM Jabalpur and Global Engineering College. So if I give you x and y coordinate here, so can I find the distance between these two? Obviously you can say yes. What is a great deal about it? I can find it and tell you what is the distance. Like, so you open the Google map. Even Google Maps show you what is the distance of the distance between these two places if you want to travel by a car, right? The road distance, it can say. So always Google Maps shows the distance is always greater than zero. It doesn't never shows you the distance between two places is less than zero. So that is called non-negativity property of the distance function. So distance function can be similar. Like if I open the Google map and say the my starting place is IIITM Jabalpur and I want to visit, let's say, Global Engineering College, the distance, let's say, is 25 kilometer. And if you start searching there, the my starting place, start of origin is Global Engineering College, and I want to visit IIITM Jabalpur. So again, same distance will be shown to you. So that is one example of symmetric function. So distance function also should be symmetric. The distance between two places x and y should be, the distance between x and y should be same as distance between y and x, right? Then transitivity property says the distance, the triangle inequality, you might have heard about in your school days. When you take, suppose this is a b c, so when you take the sum of any two sides of a triangle, that is that is always greater than or equals to the third edge of the triangle, right? So that is what is called triangle inequality. So direct distance between any two points is always lesser than if you are going through another point. So that is what is the fundamental. Let us not go more deeper into it. So what are the examples you might have already seen? So one distance, one particular case of Minkowski function is called L1 norm, or when r equals to 1. So go back and see what was the formula. So the formula one, xi minus yi to the power r whole to the power 1 by r. Now if I put the value of r equals to 1, what will be? This r is 1 and this r is 1 by 1 upon r is also 1. So this is simply sum over I varies from 1 to n xi minus yi, and that is what is called Manhattan distance, right? So Manhattan distance is, if you are from computer science or electronic discipline, then many times you might have already used Manhattan distance in many places, right? So given these two data objects, let's say x and y here are two data objects. So x value is attribute value 1 is 735, y is 326. Then what is the distance between two data points x and y? So Manhattan distance is simply take the attribute wise difference, absolute difference. So this 7 minus 3 is this, then 3 minus 2 is this, then 5 minus 6 is this. So total sum is 6. So the Manhattan distance between x and y is 6 here. So if the values are only numeric, only binary values, then Manhattan distance is also called Hamming distance. So in computer science, we say any two binary values are given, binary data is given, let's say 0, 0, 1 and 1, 0, 0. So if I say what is the Hamming distance between these two binary values, then you will say that how many bits these two binary digits are different, right? So you say here there is a difference, here there is a difference. So it's the Hamming distance is 2. So that is one example of proximity measure. So again, another one is Euclidean distance. So put the value of r equals to 2. So here it is 2 whole to the power 1 by 2. So that is what is called Euclidean distance. This is what we have learned from our school days. given these two data points X and Y, if somebody asks you what is how can you compute what is the actual distance between, or air distance between two data points X and Y, so you can compute 7 minus 3 square plus 3 minus 2 square, 5 minus 6 square, sum, take the sum of all this square, then square root of whole sum. So square root of 18 is 2.426. So this is called Euclidean distance. Another very popular measure is called Chebyshev distance, where we also call infinite norm. So this is actually infinite. So it is the maximum distance between xi minus yi. So 7 minus 3, then 3 minus 2, and 5 minus 3, attribute wise difference. They take the maximum of that. So here 7 minus 3 is 4, 3 minus 2 is 1, 5 minus 6 is also 1. So maximum among all these three is 4. So therefore, Chebyshev distance here is 4. So if you compare between Manhattan distance and Chebyshev distance, you will see that always the Manhattan distance is greater than equals to the Chebyshev distance. That is obvious, right? So these are few examples of dissimilarity measure. So till now, if you have any query, you can ask me. Then I'll move to the next session, which is the quality of clusters. Okay. If there is no question, then we can proceed. So what is this quality? Once this, suppose given a data and you identify the clusters, so how to measure two quality between the clusters formed, right? So uh, we have different brands of T-shirts, right? So you say this brand of T-shirts are better than this brands of T-shirt. So how do we measure that? How do we say that? From our past experience, we have been using that of different brands of T-shirts, and after several years of using, we know that there are some issues. Sometimes the color can change, it may not last long, the cost is too high. So depending upon that, we make our decisions that this brand is not good, that brand is better one. So similarly, given set of clusters, can you, if I ask, so what is the percentage of goodness? How do you measure? Can you say how many percentage, how good this set of this brand of T-shirts are? So then the problem will be, how do we measure? Do we have a numerical way of calculating, right? Do we have a formula to calculate that? So that is how that is what is the difficult part. Given a clusters, so how to measure which set of clusters are good? So here again, two criteria are followed. One is high intra-class similarity, or we say how cohesive the data points within a clusters are, and the low interclass similarity, where how distinctive the data points between or across the clusters, right? So these two are the main objective criteria. So cohesion should be as more as possible, and distinctiveness should be as less as more as possible. So the quality of a clustering method depends on the similarity measure used by the method, its implementation of the algorithm, its ability to discover some or all of the hidden patterns. So there are many functions exist, but it is hard to define similar enough or good enough, right? It's always a challenge. So sum of squared error, rand index, adjusted rand index, celotic coefficient, there are many ways to calculate the goodness of clusters numerically. We can give a numerical value that maybe 1 is very good clusters, 0 is a very bad cluster, 0.5 value means they are average clusters, and so on. So the cluster cohesion, there are two optimization criteria we always use. So there are two kind of measures. One is called internal measure and other one is called external measure. So in the internal measure, if class labels are not used, that is called internal measure. When you use the class labels, those measures are called external measures. So in the internal measure, uh, the cohesion and the separation. The cluster cohesion measures how closely related are objects in a cluster. So cluster separation is, this measures how distinct or well separated a cluster is from other cluster. I'll go to the second slide. It will be easy to understand. So let us see, these are the data points, right? One, in a single dimensional data, let's say it's your x-axis. On an x-axis, we have 4 data points, 1, 2, 4, and 5. This is how we have plotted on the x-axis. Now, if there is only one cluster, let's say, okay, so now you want to find all the data points in a single cluster. So we say, what is the cohesion, right? That means how closely related are objects in a cluster. So if I say I form a cluster and there is a center here, right? So from this center, suppose this is center C and this is some data point 1, data point 2, 3, 4, 5. Show how far they are from this center. This is one way of measuring the cohesion of a cluster. So here, if the data points are 1, 2, 4, 5, what is the center of this data? So 1 plus 2 plus 4 for plus 5, right? So if you find the center of this data divided by 4, so that is what is the average of the data point, or we call the centroid of the data. So that is what is 3. So 12 by 4 is 3. So now you subtract 3 minus 1 minus 3, because 3 is the center of the data, then 2 minus 3, then 4 minus 3, and 5 minus 3, right? So this is what I am calculating. Square of that is called standard square error. Okay, SSE, standard square error. So that value is 10. So now you tell me if the standard square value should be less or should be more. If it is less, then the cluster should be more cohesive. The data points are as close to the center as possible. So if this value is more, that means the data points are far away from the center of the data. Let's say there are few data points here and this is the data center. So when you calculate this square distances, so obviously it will be much more. So therefore, the SSE value will be less when data points are centered around the center of the data. They are distributed around the center of the data. So that is what is called cohesion. Then what is the separation? So separation is the center. This is a one cluster. Let's say there are different, let's say take the example of 2 clusters. So there are 2 cluster centers, right? So here, if you look at the formula, so it is the number of data points in a cluster divided by M is the center of the whole data, and MI is the center of one cluster, ith cluster. Okay. So if I have 2 clusters, right? So center of data is, let's say, M, and this is M1 and this is M2. So what I compute here is the separation is M minus Mi square divided multiplied with the weighted sum, the total number of data points in a cluster. Okay. So here in this particular example, 3 is the global cluster center, center of the data, and this 3 is the center of this cluster, particular cluster, and 4 is the total number of data points. So it is 4 multiplied with 3 minus 3 is 0. So similarly, in the next example, let us assume that data is there are 2 clusters in the data. So one cluster contains 1 and 2 data points, and the second cluster. So this is 1 and 2. Sorry. So this is 1 and 2 data points, and this is 3 and 4 data points. Okay. So now if it is the data points are 1 and 2, what is the cluster center? 1 plus 2 divided by 2, which is 1.5. It is 4 and 5. What is their cluster center? 4 plus 5 divided by 2, which is 4.5. So this is 4.5. This is 1.5. Their cluster centers. So what is the SSE values now? So SSE value is 1.5 is the cluster center. 1 minus 1.5 square plus 2 minus 1.5 square. So this is for cluster 1. And for cluster 2, 4.5 minus 4, and for 4.5 minus 5 square. So take the sum of that. This is only 1, right? Now you see which two clusters are which cluster is better. So the first one or the second one. So this is case 1 where we formed only one cluster. This is the second case where we formed two clusters, right? So obviously this is more cohesive. That means the data points are more closer to the cluster center in the second case than the first case where the data points were actually far away from the cluster center, right? Therefore the SSE value here was 10. Now it is reduces to 1. Similarly, if you now again compute the between squared sum, which is the 3 here, and 1.5 is the cluster center. So global cluster center data center is 3 minus this 1.5, right? So 3 minus 1.5, how many data points are there in this cluster? 1 and 2 multiplied with 2 plus. Here the cluster center, the data center is 3, cluster center is 4.5. So 4.5 minus 3 square into 2 because there are two data points 4 and 5 here. So this 2 comes from this. So this is 9. And now you see this case it was 0, and this case it is 9, because in the first case this clusters were all separated from the data center, and this is now again reduced. It is now increasing. So by the way, if SSE decreases, then BSS will increase, and vice versa. So here it was more, that's why it was less. Here it is less because this distance between two clusters now increasing. Therefore, SSE value is reducing and BSS value is increasing. So that is one example of how to, once clusters are formed, how to compute whether good set of clusters are formed or not numerically, right? So you can give a numerical value to say that is the percentage of goodness of clusters. So cohesion and separation, this proximity graph based approach can also be used to measure the cohesion and separation. So here in this example, if this is a cluster, these are the data points. So you can find the Euclidean distance between all pair of distances between which exist in the cluster. Take the squared sum and say that what is the SSE value. So that is what is called cohesion. So graphically you can understand in this way. So what is separation? So here you find that this is my cluster 1, this is my cluster 2. So how separated these two clusters are? So you find the all pair distances. So for example, you take this point, find the distance of this with all the data points present in the next cluster, take the square sum of that. So that is what is called separation, right? So this is how the separation is more. If it is Euclidean function, then it is good. The less is the cohesion, that is good, because this sum should be as less as possible. Lesser means the points are very close to each other. So the data points which are within a cluster, if they are very close to each other, that means the SSE value is going to be less, right? And the data points, if they are far apart from each other, the clusters are separated from each other, then that is a good thing. So separation value will be more in that case, right? So that is how is one way of measuring cohesion and separation of the goodness of the clusters. There are many different ways to do this. In fact, there exists several techniques to do this. So this is very simpler and fundamental one. So when you go more deeper into the course, you will find there are many ways to do this. So another very popular internal measure is called Siloti coefficient. So in the Siloti coefficient combines idea of both cohesion and separation, right? Instead of calculating them separately as two values, SSC and BSS, what you can do, what the Siloti coefficient does is it has combined both cohesion and uh, separation. So for an individual point, so you calculate A, which is the average distance of I to the point in its cluster. So suppose you have two clusters. So this is one point, ith point. So for every point, we calculate the Siloti coefficient. So I is the average distance of I to points in. Sorry. Is the slide visible?
Yes, yes, it's visible.
Okay. So if S equals to, so I is the average distance, A equals to average distance of I to the points in its own cluster, right? So you from this point I, sorry. So if you take from this point I, you find the distance of all the data within its own cluster. So find the average distance. So that is denoted as A. So B is average distance of I to point in all other clusters. Let's say there is another cluster here. So from I, you also find the distances. Take the average of all these distances, right? Then take the minimum. So of that, so that is again B. So B minus A. So A basically takes care of the cohesion and the B takes care of the separation. So it says B minus A divided by maximum of AB. So that is what is called Siloti coefficient. So it typically varies between 0 to 1. So if it is 1, that means the cluster set of average clusters. So this is one more example of Siloti coefficient. So I'll not go more deeper, or I'll not cover lots of this applications. Sorry, lots of internal or external measures. So that is altogether a separate study. So now we'll move to the clustering algorithms. So a cluster basically is a set of clustering is a set of clusters. So there are different ways of clustering. Many techniques exist, like in algorithms, we say there are many design techniques to solve a particular problem. We say there exists greedy method, then dynamic programming, it's a divide and conquer, right? So you have many ways also. There are many techniques exist for clustering. So very popular one is partitional clustering, hierarchical clustering, density-based clustering, graph-based clustering, and many more. So today's lecture we will see about partitional clustering. So if you have more interest, you can explore more literatures on other types of clustering. So in the partitional clustering, given the set of data objects, so here the data points are original data points. So we divide the data, we partition the data into different clusters. So how can we partition the data? So we take some points and then we form the clusters around those points, right? Those are called, let's say, centroids. So around the centroid, we will form the clusters. So if you use those centroids to form the clusters, and the points which are closer to the centroid will assign those points into the cluster, then such kind or such techniques is called partitional clustering. Then in the hierarchical clustering, Traditional hierarchical clustering, we form the hierarchies, right? So in the academics establishments, let's say we also have hierarchies of positions. So we have directors. So if you consider them set of employees, and in the set of employees, we have two hierarchies. Let's say set of faculties and set of staffs. So, and then again within the group of faculties, we have again different hierarchies. So it's within the faculties you have professors, associate professors, and assistant professors. Again, in that hierarchy, we have again established, among the set of professors, we have senior professors and then professors. So on in assistants. Again, we have different we categorize senior assistant professors and assistant professors. So we can categorize. So that is a set of hierarchies, right? So we form, if you can form the clusters based on the hierarchy, you can take again, let us consider the animal kingdom. So if you look at the animal kingdom, we have the set of families, right? And a small set of family is included in a larger set of family in the animal kingdom, and a whole animal kingdom is can be considered as a single family. So that is one example of a hierarchy. So if I give you the data of all the animal kingdom, so can you able to find the set of clusters within them? That means a set of animals, one set of animals should be in a single cluster. So there the hierarchical clustering algorithm will be more useful, because the data is hierarchy in inherent hierarchy exists in the animal kingdom. So clusters can be of various types. So it's well-separated clusters, center-based clusters, contiguous clusters, density-based clusters, property or conceptual clusters, and so on. So well separated clusters, you can see these three colors represents three clusters. So here we say these three clusters are well separated, because a cluster is a set of points such that any point in a cluster is closer or more similar to every other point in the cluster than to any point. So if you take any point within this cluster, right, so that cluster, that point is closer to any other point within the cluster as compared to point in any other cluster. If this property satisfies in a clustering, then such clustering is called well separated. Then what is center-based clustering? So in the center-based clustering, if you take the data points, so this set of clusters, there are 4 clusters here exist in the data. So this is what is my entire data. And within the data, there are 4 clusters have I identified. And if I say, is this set of clusters well separated? The answer is no. Why? Because if you take these 2 data points, let's say, and this data points and this data points and this data points, let's say, so if find distance between these two data points is greater than the distance between these two data points, whereas these data points 1 and 2 are in two different clusters. So therefore, this is not one example of a well separated cluster. So this kind of cluster formation is called center-based clustering. Why this is called center-based clustering? Because, or we also centroids are also called prototypes. Why? Because the definition says all the data points within a cluster are more closer to a center than to any other center. So if this is the center C1 and this is center C2, then if you look at this any data points now here, so you find this data point is more closer to its own cluster center as compared to cluster center of any other cluster, right? Cluster center of this cluster. So therefore, this kind of cluster set of clusters are called center-based clustering or prototype-based clustering. So what is continuity-based clustering? So a cluster is a set of points such that a point in a cluster is closer or more similar to one or more other points in the cluster than to any point in the cluster. So in this data, if you look at, so there are how many clusters? 1, 2, 3, 4, 5, 6, 7, and 8 clusters are visible here. So if you look at, is there OL separated? The answer is obviously no. So if you look at these two data points, they are more closer to each other than this and this. So is this is this set of clusters centered west? Again, no, right? If you look at the centers, centered west, the data points more closer to its own cluster center, then again the obvious answer is no, because if you look at this, its center will be somewhere here, and if you look at the center here, then probably these two are more closer than somewhere data point centers are here. So again, that does centered based clustering is not satisfied in this data. The center of data can be here, the center of this cluster can be here. So if you look at this, these two data points are more closer, centers are more closer to each other than this and this. So this data points and its center is far away, whereas this data points and this cluster center is more closer to each other, right? Therefore, this set of clusters are also not centered based. So it is continuity based, because if you look at the data points, you find its immediate neighbors, some points in its own neighbors, in its own proximity, which are more closer. So if you look at this data point here and some data point here, so why they are related? It looks like they are far apart from each other. And if you look at a point here and a point here, so you see these data points are far apart from each other. So this data point, so this data point should have gone with this data, because this is more closer. So why this data and this data, these two data points are closer to each other, or they are within a single cluster? Because you find a data here which is more closer. Again, you find another point in its own proximity. So another point which is in own proximity, and so on. So they make a connectivity between them. So therefore, this makes a connection. So therefore, it is called a connectivity-based clustering. So if you look at them, so it makes a connectivity like this. Therefore, this is one example of continuity-based clustering. So what is density-based clustering? So what is the density? So density is, as you know from your school days, the density is the number of objects within a unit sphere, or within a unit cube. So that is what is called density. So based on that, how many data points are there in a unit area, in a unit region, can you able to find out the clusters? So that if some cluster means the data points should have similar density, so they should form the clusters. So based on the density, if you form the clusters, such clusters will be called density based clustering, right? So similar density regions form the clusters. So if you look at the previous data, the previous example, so in this example, uh, so in this example, the same data set was given, whereas this two set of data points are connected and becomes one cluster. All these data points are identified as clusters. But if we look at the next figure, so the beauty of this is, these two data were now separated. These two are now two different clusters, and the connection between them are not counted now. And these three clusters that we had seen previously, those are also gone from here. Why? Because in density based clustering, we say the data points having very less density, so those are possibly noise points or outlier points, right? So what is the definition of outlier? Many times in our community we say, if something we say in our class, if a student is exceptional, we say he is the outlier of my class, right? So if a student is very bad, we say don't look at him, he's outlier. So that is how we say the outlier of things, right? It is something, his distribution, right? This characteristic is quite different than the average of the data, or of the average population, right? So we say those are the outliers. Something is very good, exceptional than the entire population, we say that is outlier, or we say sometimes say it's an outstanding student. So Here we say some data points which are outlier. That means those are far away from the other data points. So if a data points exists here, we say obviously that is an outlier. It is not very close to any data. So its density will be almost zero, right? So you find no data point around this or very few data points around a data point. So its density will be very less, right? So if a data point exists here and around that there are lots of data, so you say the density of data points is very high, so it cannot be outlier. If the density is very less, almost zero, we say data points is outlier. So in this density based clustering, the main advantage is along with the clusters, we also can identify the outliers and noisy data points, right? And can separate them from the data. So in this the slide, we had seen several clusters. Now these three are gone in the were removed because those data points density is very less, because every data point's neighborhood is very less. In the close proximity of any data points, uh, you hardly find any other data points. So therefore, the density is very less, almost zero. So those data points are identified as outliers, and the data is removed. The outliers are removed from the data. So that is one of the pre-processing steps. We do this in the machine learning algorithms, right? How to clean the data. So one is the missing value is given. So how to identify those values? Suppose sometimes we fail to measure the data somewhere. The reading is not proper. Something happened, so reading is not taken properly. So that is missing data. Sometimes the outlier noise data has to be identified and removed from the data. Sometimes we do the scaling of the data. So those are basically pre-processing steps in any machine learning techniques. So this density-based clustering can do that. So they are very popular because they can identify the outliers and noise in the data. Then uh, so in the cluster analysis, we have partitioning criteria, the separation of clusters, similarity measure. So then another criteria can be suppose your dimension. So you take n dimensional data, your dimension can be 1000. So when you have set of genes, so every genes in your body, they are correlated with each other. So when some disease happen to you, let's say we have fever, so some set of genes can co-express with each other. So if you study there, we call gene expression. So some set of genes co-express themselves, right? So when we have, let's say, fever, some set of genes can co-express themselves by looking at their expressions. So you say, so this set of genes are correlated. So when fever happened, this set of genes are should be regulated. So we design the drugs depending upon the expressions of some set of genes. So we give a drugs, you take a pill, and then your fever reduces. Why that is so? Because some set of genes are regulated through that tablet, through that pill, right? So that is what. So if you look at the data, so the data dimension is sometimes 1000, 2000, 5000 is the dimension. It is sometimes huge. So you might have already heard about curse of dimensionality. What is curse of dimensionality? If the data is huge, finding the similarity between data points is a challenging task. Therefore, since we cannot able to identify that, so then the next question obviously will be, can we identify which dimensions are not very relevant to us? Can you reduce such dimensions, right? So that is called dimensionality reduction problem. So sometimes you do the clustering on the whole dimension, sometimes we also reduce the dimension. So in the study of machine learning, dimensionality reduction itself is a separate branch, right? So course of dimensionality, if you search course of dimensionality, you will find a lot of literature about that. Today's talk is not going to cover that. So that is one of the things we usually consider in the clustering process. So what are the challenges in the clustering? So discovery of clusters with arbitrary shape. So shape of the clusters formation can be of any shape, right? ability to deal with noisy data. So data can contain outliers and noise. So how to identify the clusters within such a data? Incremental clustering and incentive to input order. So the way the data is supplied, which one is object one, which one is object two, which one is object three, and so on. So clustering algorithms should not depend upon the input order of the data, the course of dimensionality, and so on. So there are many clustering approaches I have already told you. So we'll see the partitioning approach. So one algorithm we will see there, right? So if you have any query till now, you can ask me. Otherwise, I'll go to the next section. Okay. I assume there is no queries. So in the partitioning approach, K-means is a very popular clustering algorithm. So KNN you have already seen. So it's very similar to KNN. KNN is used for classification, and this K-means is a popular algorithm in clustering. So this was found sometimes in 1950s by multiple researchers independently. Official documentation or published result points to Steinhaus as the first author algorithm. So credit goes to him because he published the result. Otherwise, the many researchers parallelly probably developed this algorithm. So we'll see this in the K-means is a very easy algorithm to understand, very easy to code, and the computational complexity is very less. Therefore, it's a very highly popular algorithm. Along with one or two, if you look at the clustering literature or in the applications, you'll find three, four algorithms are very popular. One among them is K-means, other is DB-scan, and one more algorithm is hierarchical. So these three algorithms are widely used. You can find the code in the Python libraries also. So today's lab session, you will also see this implementation of K-means algorithms and its challenges. So this is a partitional clustering approach. Here K, what is the K means? So there are two terms, K and means. So K stands for number of clusters. So we assume that the number of clusters within the data is known to us previously. That means we have the domain knowledge to say what is the value of K, how many groups you want to identify, right? How many groups you want to discover from the data. So that has to be supplied by the user. Each cluster is associated with the centroid, or we call center point or mean of the data point. Right? Like so, centered or mean or centroid. So the two terms k means k is the number of data points, means is the arithmetic mean of the data points. Therefore, this clustering algorithm is called k-means clustering. So each point is assigned to the cluster with the closest centroid. So the basic algorithm is very simple, which is given below. So k points as the initial cluster center. So let us assume we have a two-dimensional space, and some data points are given like this. So now what happened is, let's say somebody tell you that there are three clusters exist in the data. So what you can do is you first arbitrarily choose any three random points as cluster centers. So let's say take this was as C1, this as C2, and this as C3. So you choose any three data points as cluster centers. Okay. So what is the next step of the algorithm? Next step of the algorithm is you then find the distance of each data points to these three cluster centers. Now you pick a data point. Suppose I pick this data point. For this data point, I find the distance from C1, distance from C2, and distance from C3, right? And clearly, the distance of this data point from C3 is closer as compared to C1 and C2. Therefore, this is assigned to the cluster whose cluster center is C3. Similarly, if I take this data point, then I find the distance of this data point from C1, C2, and C3. So clearly, the distance of this data from, as if you compare between C1, C2, and C3, the distance of this data point from C1 is more closer as compared to C2 and C3. Therefore, this data point will go to the cluster being cluster center C1. So that way we continue for all the data points, all n data points, right? So there are n k cluster centers. So for k clusters, you find for you take a point x and find distance with C1, C2 up to Ck, and whichever is the minimum, so you assign x to that cluster center, right? That way the three clusters will be formed. Most likely this is 1, this is 2, and this is 3. So three different clusters will be formed. So this is called one run of the algorithm, only one iteration of the algorithm. And this, once three clusters are formed, so what you do is, now there are, suppose there are suppose there are what is I called n1 data points here, n2 data points in cluster 2, and n3 data points in cluster 3. So now what you can do, take this n1 data point, find their arithmetic mean, right? For example, if one data point is 2 3, other data points is 4 5, another data points is 6 7. So now can somebody say what is the center of these three data points? Might have done this in your class 5th or class 6th. So what is the center of these data points? So you would say 2 plus 4 plus 6, right? So it is 12 divided by 3, which is 6. Then take 3 plus 5 plus 7, 8 plus 7, 15. 15 divided by 3, because there are 3 data points, so which is something 5 point, some value will come, right? So this is what is the center of the data. So you find the center of the data, that is my new cluster center C1. Similarly, for this data point, you find a new cluster center called this C2, and for this set of data points, you find a new cluster center C3. So clearly, if you look at this, the cluster center may not be an actual data points. It is just the arithmetic mean of the data. So therefore, it may not be the actual data point. It may not be. Most likely, it will not be a actual data point. That is not an issue. Then repeat the same process again for the data, right? And continue doing this again and again till the cluster center remains static. That means, suppose in iteration 2, you recompute the cluster center, then again in iteration 3, again recompute the cluster center. Suppose still cluster center are changing, then again apply one more iteration. Let us say in the iteration 4, cluster center are again changing, and let's say in repetition in the iteration 4, the cluster center are not changing. So at that point, you stop the iteration. No need to move this further. Let us see this through one example. So this is one example of a set of data points. So three cluster centers are chosen randomly. Here is one, here is one. This is a random sampling of data, right? So you do not know which data points are in one cluster. So if you visualize this, probably one way of saying this is this should be in one cluster. This set of data points should be one, and this set of data points are nearby, so they should be in one cluster. But let us take three cluster centers randomly, which are 1 2 3 taken here, marked as plus symbol. So then in the next iteration, compute all the data points which are closer to their cluster center. So you find all these data points which are closer to this set of data points will be closer to this data points also will be closer to this cluster, and this data points is more closer to this cluster, therefore it is assigned. So if you look at this, I have three clusters, so this is one cluster, so different color represents different clusters. So there are three clusters for me. So now look at the green data points. So if you recompute their cluster center, the arithmetic mean of all the data points, you will find that obviously that will move towards somewhere here, and somewhere here the cluster center will be formed. So we look at the blue data points. So their distribution is something, so that when you find the mean, so you find the mean will be somewhere around here, right? And this data points, the cluster center will be somewhere here. So when you recompute the cluster centers, so what exactly happened? So look at, sorry. Now you look at, this was our initial cluster centers. So in the next iteration, I have these cluster centers, right? So this cluster center is moving, data points are getting redistributed, they are moving from one cluster to the other, right? And in the third iteration, when you again apply the same algorithm, so you find that again the cluster centers are moving. Look at, this is moving in this direction, this is moving here, and this is moving here, right? And the number of data points also are moving. Look at these two steps. So boundary is drawn, but it is now moving. This data points were previously in the blue cluster, they are going here. This data points were there in the green cluster, they are also moving to this cluster, and so on. So now keep on doing this, repeat this process till the cluster centers are fixed. Now after this is the previous step, and the next step, when you recompute the cluster center, it is just moving. And now after iteration 6, if you apply again the same algorithm, we will find that cluster center will not change its position. And if the cluster center doesn't change its position, then the data or the data points or the objects within that cluster also is not going to be redistributed. They are not going to move from one cluster to the other. Therefore, that is where is the stopping criteria. The algorithm stops there. Okay? So this is one example. So initial centroids are often chosen randomly, right? So clusters produced vary from one run of the algorithm to the other because cluster centers are chosen randomly. So if you vary the cluster centers in the next time or next user takes, since it's the random, so you pick set of cluster centers in first run of your algorithm. In the second time, if you have another application on the same data, you again can choose another set of cluster centers. So the clusters that is produced every time you run the k-means algorithm can vary with each other, right? The set of clusters formation can vary from each run of the algorithm. The centroid is the mean of the point in the cluster. Closeness is measured by Euclidean distance, cosine similarity, correlation, or any distance functions that you use. K-means will converge for common similarity measures mentioned above. Right. So the main point, another important point is complexity, time complexity of the algorithm is NKID. What is N? N is the number of data objects. K is the number of clusters in the data. I is the how many number of iterations K means is applied. D is the dimension of the data. Okay? So when we assume that D is very less as compared to N, because number of data points is usually much more than the dimension of the data, and the number of clusters also is very less as compared to the dimension of, as compared to the number of data points. Let's say the data can contain 1 million or 1 billion data points, but the number of clusters within that can be in hundreds only, right? So therefore k value can be very less, So number of iterations usually varies between maximum 10. Many a times we have seen this. So these values can be very less as compared to n. Therefore, this can be something b of n, right? So many times people say it's the linear time complexity, nearly linear time complexity algorithm, because n is the number of data points and d is the dimension. Otherwise, you would mention this as n cross d. That is what is the size of the data. Therefore, the complexity of the algorithm is linear, nearly linear. But sometimes the I value can be huge. It can be more than 100 iterations. But in real life applications, hardly it happens. Then K value also can be huge. But then if you consider them as constants, then it is order of n cross d, which is nearly linear. So it's a very fast algorithm. Therefore, it is very popular. So how do we evaluate how good the clusterings are? We have already seen SSE. So given the cluster centers, you can find the SSE values, right? You can subtract all the difference between the cluster center and the data points within a cluster, take the square sum of that, continue that for all the clusters. So that is what is called SSE, sum of square data for the k-means clustering. So see now what happened. The same data is taken and k-means is applied, giving taking two different cluster centers, right? So one case, this kind of clusters are found, which are actually correct because this is what is the actual clusters in the data, true level of the clusters. And this exact almost similar clusters are found except these two data points, right? These two data points actually are misclassified. This would have gone to the green cluster. Instead, they are assigned to the blue cluster. Now, if a different different cluster centers are chosen, then the same data, the k-means can produce these clusters also. So if you actually compare this with the original data distribution, you find this set of clusters are not good at all. No way those are good, because these two clusters are actually merged into a single cluster, right? So this is probably why this is happening, because k-means has a problem whose clusters are of different sizes. One cluster is very big, another cluster is smaller one, right? So let's say this is one cluster, this is one cluster, and this is one cluster. This is what is the data. So if you apply k-means property says it will form the clusters around the cluster center. Therefore, larger or bigger clusters will get splitted and smaller cluster will be merged with larger clusters, right? So that is what is the problem with the k-means. Another is density distribution is different, then the k-means will fail. Another is known globular set, because how the data points are getting assigned to a cluster. If you have a cluster center C, you take some data points, another cluster center C1, you have set certain data points. So you find the distance of all the data points with their cluster centers, see which cluster center is the closest, then you assign such data points to the nearby cluster centers. That is what is k-means. So what happened here is, since data points are attracted to or are assigned to its nearer cluster center, so what exactly happened? Some globular or spherical shaped clusters are formed, right? So if a cluster is like this, let's say, this kind of clusters are never going to be identified by the k-means, because wherever you take the cluster center, if you take, suppose there is another cluster in the data like this, right? So these two are the clusters. So if you take even the cluster center here, you see what happened. This data point or one cluster center here. So what exactly will happen? So this data points will be attracted towards this cluster center. This data points also will go on with this cluster center, and this data, all these data points will go to this cluster center C1, and this data point will go towards cluster center C2. So it's always a challenge to identify arbitrary shape or non-globular shape clusters. Is very useful when the clusters, the shape of the clusters is spherical, right, or globular. If it is arbitrary shape cluster, then K means fail miserably. So this is one example of different sizes. So if you look at this data distribution, you find this cluster is much bigger as compared to these two smaller clusters. So if you apply K means here, so whichever way you apply K means, giving K value as 3, so you can never able to, K means will is never going to produce these 3 actual clusters, because this larger cluster will be splitted among, distributed among smaller clusters. So this way you see the cluster, how these clusters are formed. So this data points are going to this cluster and this cluster now, right? So these clusters are not appropriate clusters. This happens because the data points are getting assigned to its nearby cluster center. Then different density, you see these two clusters, they are of high density, and this cluster, if you look at, this is of low density region, right? This is a sparse region. These two are dense regions because the points are much closer to each other. Okay. So even if you look at the Jabalpur city, some places are there which are highly dense, and some places are there which are highly sparse, right? Population density, we say population density. So some regions population density is too high, and some regions population density is too less. So that is what is the density, number of persons within a unit radius. So here, if you apply K means, again K means is not going to capture the density distribution of the data, and most likely these 3 clusters are formed, green, blue, and red. So which again is a not appropriate clusters, because this data point should go to different clusters where they merge, and this set of data should have gone to a single cluster, whereas this is split into 2. Then non-globular, so clearly these two clusters, if you see, these are non-globular shape clusters, right? So this is not spherical. So again, if you apply K means again will fail miserably wherever you take the irrespective of the center, initial cluster centers chosen. So best way can be, this is one cluster center, this is one cluster center. So these data points are more closer to this cluster center than this. So this is where these two clusters are redistributed, right? So this is not at all appropriate clustering. So we can also overcome the K-means limitation. There are many improvements proposed in the literature, right? There are algorithms, K-means plus algorithms, and there are many ways to choose the initial cluster centers. So there are many ways you can handle. So one of the way is handling the clustering is use many clusters. So instead of forming just 3 cluster in this data, if we form more than 3 from the data, then what happened is there is no issue, because at least we make sure that the clusters we are forming, they, all the data points, objects within that cluster are from a single cluster only. So if you look at this cluster probably is this now, and this set of data points are this, and this cluster is splitted into many. So if you pick any cluster here, let's say if you pick this cluster, see all the data points within this cluster, they belongs to a single larger cluster only, right? So this way K-means will work. It will split the larger clusters into many smaller clusters. So you can SSE value which will be much lesser, right? So if the number of clusters is more, you apply the K-means with the K value much greater, then the SSE value will be lesser. So better clusters are formed. Then this kind of data you see, it was a failure there, arbitrary shape clusters. But here if you see any data, any clusters if you pick, you see this has all the data points within these clusters are from a single cluster only, right? These data points are all from this cluster. Then these data points are from this red cluster and so on. So this is one way. So second is how to choose the initial cluster centroid. So this is one example where three cluster centers are chosen. This example we have already seen. So we have seen that all these data points, the actual clusters are formed except these two. Now see one more example where if you choose the cluster centers like this, one is here, one is here, and one is here, because randomly we are picking the cluster centers. So if you pick the cluster centers, how these elements, how these objects are going to be assigned to their cluster center. So this is the first iteration. This cluster center is moving here. This cluster center has moved to this, and this cluster center has moved to this. Because of this, now in the next iteration, you see what is happening. This is not getting changed. These two cluster centers are now getting changed. So because of that, what is happening is these three clusters are formed. So these two clusters are merged into a single one, and these two clusters are now split. This larger cluster is split into two. Same data, only because we choose two different set of cluster centers. So we have two different clusters, two set of clusters. One is that we have seen in the previous case, and other one is this. First case was a better clustering. Second case was is not appropriate clustering. So, problem with selecting initial cluster centers, the probability of choosing. So, this case may not arise if you choose one cluster center from every cluster. There are three clusters. So, if you choose in the first case, if you go back and see the first case, what you see is we choose the cluster centers which are closer to the actual clusters. So because of this, actual clusters were formed. So most likely, if you choose cluster center, one from this cluster, one from this cluster, and one from this cluster, so K means can able to produce good clusters. So what is the probability of choosing one cluster center from each cluster? So chance is relatively small when K value is large. So the probability of choosing one cluster center from every cluster is number of ways to select one centroid from each cluster. There are n number of data points. So assume that any data point can go to any cluster. So this is k factorial 1 n to the power k, and number of ways to select k centroids is k n to the power k. So if you simplify this down, this is actually k factorial divided by k to the power k, where k factorial is much smaller than k to the power k, right? So therefore, if k is 10, the probability of choosing one cluster center from every cluster is 10 factorial by 10 to the power 10, which is 0.0003, which is highly negligible, right? So if the number of clusters are 100, then this is even negligible. So it's a high probability that when you choose the cluster centers randomly, there is high probability that your cluster centers will not be chosen from each and every cluster, right? It may happen that many cluster centers will be chosen from a single cluster, and many clusters will not contribute any cluster center. So this is one example. What will happen if you do not take this one? So this is with two initial centroid in one cluster of each pair. There are 10 number of clusters actually, right? So out of that, what we have done, we have chosen two cluster center in a single cluster here, two here, two here, two here, and two here. This cluster, no cluster center is chosen. For this cluster, this, and this. for all 5 clusters. No cluster center is chosen, and we have taken actually 10 cluster centers from 5 cluster centers. So what exactly happened because of that? So now if we look at this, we will see that how this is moving. Initially we chosen 10 cluster centers from different 5 different clusters. So randomly now we see how it is moving, getting redistributed, right? So in this case, actual clusters are found because cluster centers are moving in the right direction. So because of that, 10 clusters are found. Now if we look at other thing, other example, now you see the same thing starting with some pair clusters is having 3 initial centroids. So here if you look at some clusters having uh, 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 here there are 2 cluster centers. Here it is one, here it is one, here it is one, here it is one, 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 and one. uh, it's not. Okay, so here for this two, one cluster center is chosen, and here for this two is chosen. Here it is two. Here it is two, and here it is one. So for this clusters, only one cluster center is chosen, and here it within a cluster, 2 cluster centers are chosen. So if you take this example, the same data and different cluster centers, then you will see that when you form the clusters, the uh, the example actually is there some take this one. So this is how we started, and this is the set of clusters that were formed. Now you see these 2 clusters are merged into a single one, and this cluster is split into two, right? And all others are fine. So same example where different cluster centers are chosen from different clusters, and this is what is happening there. So if you can somehow choose the cluster centers from every cluster, so the good clusters can be formed. So solution to initial cluster center problem is there are many ways pre-processing step exists. So first is apply multiple runs. So K means usually is not run only once. You run the algorithm given the data. So run once K means find out the clusters, then again run K means, then again find out the set of clusters, then again run K means. So at least 10 times you run the K means. Take the SSE value at each step. If the SSE value is lowest for whichever run, so say that that is the best clusters produced by the k-means algorithm. That is one of the way to handle the initial cluster center problem. So select more than k initial centroid, and then once you form the smaller clusters, then you can merge the smaller clusters to form the actual clusters. That is again a tedious thing. Then in the post processing, generate a large number of clusters and then perform a hierarchical clustering algorithm to combine them all. Another way is there are many other techniques exist which are called k bisecting k-means algorithm. Other algorithm is called k-means plus plus. Then there are also other techniques exist how to identify the cluster centers properly given the data, given any kind of data distribution. So can you identify the cluster centers in the data, so somehow, so that those cluster centers can be used for k-means algorithm. So can I able to supply that? So you first apply a pre-processing algorithm, right? Suppose this data is given, and say your pre-processing algorithm says this is one cluster center and this is one cluster center. Now you apply k-means. So if you then apply k-means, probably the data will be split into this way. This will be my cluster 1 and this is cluster 2. So two set of clusters will be formed in this case. So that those are many algorithms exist. We have been also working. If you look at the journals, then you will find decay means algorithm is proposed by my students, which actually identifies the which actually take care of this centered initial centered problem. We can identify the k cluster centers which are far apart from each other, which are well separated from each other. What exactly is the problem? So given the data, if you take the cluster center which are suppose in this data you want to find two clusters, so you have to supply two cluster centers, k is 2. So it by chance if you choose these two cluster centers, two data points which are very close to each other, then obviously the clusters are not will not be formed properly, will form very bad clusters. So probably these 3 4 data points will go here and all remaining data points will go to these clusters. So the bad clusters are going to be formed. So the way the you choose the cluster centers which are actually far apart from each other. So instead of that, if you choose this and this data points as two cluster centers, then most likely the data is going to be split in this way. One set of data should go to this cluster center and other set of data points will go to this cluster center, and it will settle like this. So that is a better way of finding the cluster centers, right? There are many algorithms exist in the literature, so you can look at the k-means plus algorithm to find out how the cluster centers are identified. Then obviously the disadvantage of applying such techniques, such pre-processing steps, is the complexity increases, because k-means is very popular because it is very fast. So if you go for pre-processing steps, the value the algorithm has more complexity, right? So that complexity will be added as a pre-processing step. So you have to spend more time, but your k-means is going to be faster because number of iterations is in the k-means is going to be less, right? So if you have, I should conclude here. So if you have any queries, now you can ask me. Otherwise, we can conclude the session. Any question from audience?
No questions. There will be no question maybe.
Okay,
Thank,
then we can conclude. Thank
thank,
you all
thank,
for being
thank
present.
thank you, Dr. Mahanti, for your nice presentation. So, thank you for giving your valuable time for delivering a lecture in this FDP. I think it will be clear for all participants about the clustering algorithm. They may come to know that how to use the clustering algorithms in, in different areas of the machine learning. So, thank you once again.
Okay, you have any queries at latter part? You have any doubt? We can communicate through emails. Thank you all.
Okay, thank you.
I
Thank
should
you
leave.
once again.